I'd like to show you an example problem illustrating how a Brayton cycle works. A Brayton cycle with irreversibility is used to model a very traditional gas turbine engine. So let's get started. So this is a basic schematic of what a Brayton cycle looks like. And here's what I'd like to cover in this video. First is let's just look at a very quick crash course on what a Brayton cycle is all about and what we're trying to model with the Brayton cycle. The example problem I've come up with requires some background, a little bit of a story, which I'll give you, and then we'll get into the details and the numerical evaluation of an air standard Brayton cycle analysis, where we use the ideal gas with variable specific heat model, and then we'll repeat exactly the same problem using the constant specific heat model, and then compare the results. So here's our crash course on the air standard Brayton cycle. Oops, I missed a slide. Now we're back to where this is a cutaway view of what's called a stationary gas turbine engine, and it is used to drive an electric power generator. And so this cutaway gives us a chance to sort of look at the equipment involved in a gas turbine engine, its multiple components in that engine. Here at state one is the inlet to an axial compressor. Look at these multiple stages where the air comes in the inlet, and stage by stage by stage, the pressure of the air is built up and increased and increased and increased until we go into a combustion chamber. And for the thermodynamic cycle, we model the combustion process by heat addition. So, of course, in combustion, we're adding fuel and air, lighting it off for combustion, high release of energy. In our thermodynamic model, we're simply adding heat to the air. Now, so that very, very hot air is going into, for this example, 1, 2, 3 stages of turbine, of an air turbine. And so that's spinning the rotor. And so much of the power is going to drive the compressor, but the power that's left over, the excess power, is going to drive the electric generator. And so then out from this 3-stage turbine process is the exhaust gas. Hot exhaust gas goes out to the surroundings. So that's a general idea of the equipment associated with a stationary gas turbine engine. And here's the textbook sketch depicting what we just saw in cutaway view. Here's the compressor coming in at state 1, air coming in at state 1 to the compressor, increasing the pressure to state 2, going into a heat exchanger. This is the model of the combustion chamber where we're adding heat. State 3 goes into the inlet of the turbine. State 4 leaving the turbine. And of course, see, this turbine is making power that goes in 2 directions. One is the net power going to, say, run a generator or some type of rotating equipment, but also there's power going to drive the compressor. Now, for our thermodynamic model, process 4 to 1, we consider to be rejecting heat from the air so we can get back into the compressor and complete our cycle. So let's compare and contrast the Brayton thermodynamic cycle with a gas turbine engine. So in the compressor section, well, both of these are well modeled by an adiabatic process. In most cases, in the real world, it's an adiabatic and irreversible process that we'll deal with. The heat addition process, well, for the Brayton cycle, we model that as constant pressure heat addition, where no work is involved. In the gas turbine engine, that's where the combustion chamber is. The turbine section, similar remarks as the compressor section. Both of these situations are characterized by adiabatic processes. And then finally, at the turbine exit, in the Brayton cycle, we reject heat from the air so that we can return to the inlet of the compressor. But in the gas turbine engine, we simply exhaust our hot exhaust out to the surroundings. Okay, and so it's logical. I think you're getting the idea of all these cycle analyses that we're going to be drawing, particularly for the open system analyses, a TS diagram. So here's our TS diagram for the Brayton cycle. Notice here I've got two lines of constant pressure called isobars. Here's the low pressure, P1 equals P4, and here's the higher pressure. Now, an important thing to observe is that the higher pressure isobar is a steeper curve than the lower pressure isobar. Okay, we'll look at, so inlet to the compressor, state 1. If the compressor were reversible and adiabatic, we'd go to state 2I, but we realize that in the real world, there are irreversibilities associated with the compression process that even though it's adiabatic, and so we're going to state 2A, to actual, through a dashed line. Here's our heat addition process, 2A to 3, where we're adding heat to the air in the cycle. So we're the pressure stays the same, but we're dramatically increasing the temperature. We come into the turbine. If the turbine had been reversible and adiabatic, we would go down in the isentropic process to state 4I, but we realize in the real world there is unrestrained expansion associated with that turbine, so we go through this dashed line, the irreversible adiabatic turbine, to state 4A. So that gives you a general idea, TS diagram, for the Brayton cycle. If you do enough of these, this TS diagram is going to be right impressed in your head. Now, just some reminder fundamentals about the Brayton cycle. You've seen the cutaway view of the gas turbine engine. You've seen the schematic. Well, reminder is when we're analyzing the Brayton cycle, we're going to be analyzing open system components. Steady state, steady flow, one inlet, one outlet, open system components. Realize that what we're doing is we're using a thermodynamic model to model a gas turbine engine. So recognize that similarly, for the gas turbine engine, the combustion process of adding fuel and air together and getting heat output, we're modeling by adding heat at a certain rate, Q dot. Let's see, here is the reminder over here on the left, the reminder of our system operating in a cycle. So the Brayton cycle would be located within this little black box, rotating, making net power, showing the clockwise rotation, making net power, taking in high temperature heat transfer from a high temperature reservoir and rejecting heat to a lower temperature reservoir. And then finally, remember the thermal efficiency of the cycle is the energy sought over the energy that costs. And if we divide everything by m dot, we simply get the thermal efficiency is little W net divided by little QH. Now, depending on the section you're in, this may or may not be a new definition of a performance measure for gas turbine engines, called the back work ratio. So as I drop down and I go to Wikipedia or Google University and say, what's the back work ratio in the Brayton cycle? Well, it's the fraction of work produced by the turbine, here's the turbine, okay, divided by the fraction produced by the turbine that's consumed by the compressor. So do you see that the compressor is consuming this much work? So here's a visualization. This height right here is a visualization of the work produced by the turbine, W dot over M dot. But over here, this line here is a visualization of the work needed by the compressor. So the net work will be the difference between these two. Back work ratio for gas turbine engines is historically very high. Now a little story to tell you about the coming up example problem, and it has to do with the USS Freedom class high-speed warships. I had the opportunity at an event to hear a presentation by a Virginia Tech graduate who is now an executive vice president of Rolls-Royce engines. And he was talking about some of his major projects at Rolls-Royce. And one of his major projects has been the design and implementation of Rolls-Royce gas turbine engines to propel for the propulsion system for this USS Freedom class warship. So why is this important? So here's some great images of the Freedom class warship, and the rated speed, the maximum speed of this ship is 47 knots. In other words, 54 miles per hour. Imagine that. Imagine a ship this size going through the water at 54 miles an hour. That's incredible. Well, how do we pull that off? Well, so the presenter, the Virginia Tech graduate, mentioned that on one of his major projects was the design and implementation of two Rolls-Royce gas turbine engines, each of them rated at 48,000 horsepower. That's just incredible to me. 48,000 horsepower per engine times two. Here's a view of what one of these Rolls-Royce MT-30 gas turbine engines looks like on board within that ship. Here's the inlet air going into the compressor section, okay? The traditional components, this would be the turbine section, okay? And then here's the shaft that's going to go to drive the propulsion system for the ship, 48,000 horsepower net output from the shaft. And then, of course, the hot exhaust gas is simply going exhausted out to the surroundings. Here's a view then of this MT-30 gas turbine engine by itself with the inlet and exhaust outlet. And let me just encourage you to click on these links to look at pretty cool YouTube videos about this information. This warship, the USS Freedom class warship, is driven by a water jet propulsion system, which is just like a jet ski, except a lot bigger. And so here is a little bit of a schematic of what the propulsion system for this warship looks like. It's a water jet. And so here is a sort of a little view of the engine, rotating shaft, and driving this water jet pump, creating the water jet that's driving the ship through the ocean. And now we get to our example problem. And so you're going to be able to, you can work this with your skills now. You can work through and do the analysis required to study this Brayton cycle model of this Rolls-Royce engine. Here we go. An air standard Brayton cycle delivers 48,000 horsepower of net rotating power for the USS Freedom high-speed combat ship's propulsion system. The inlet conditions of the compressor are 100 kPa, 1 atmosphere, and 290 K, room temperature. The compressor pressure ratio is 32, so the outlet pressure is 32 times the inlet pressure of the compressor. The turbine section inlet temperature in the cycle, so what's going into the turbine, 1300 degrees K. The compressor efficiency is 85%, and the turbine efficiency is 87%. And for this example problem, let's model air as an ideal gas with variable specific heat. And here in our analysis, this is what we need to find. To make 48,000 horsepower, we need to figure out the mass flow of air required. We want to figure out the rate of heat addition. That would be to calculate the fuel rate needed to run the engine. The back work ratio, in other words, the power required to drive the compressor section divided by the total output of the turbine. And then finally, the engine's thermal efficiency, energy sought over the energy that costs. So let's start with a sketch, okay? And so we've got two sketches here on one slide. Here would be the components going into the compressor 1, out of the compressor 2, the heat addition process into the turbine at 3 and out of the turbine at 4. And here's the TS diagram. Okay, we're going to blaze through that because I'm hoping you've got some experience, right? So the compressor is not exactly reversible and adiabatic. It's adiabatic and irreversible. That's why we have this process 1 to 2A. So we're going to need to determine state 2A with the given information. Okay. Then state 3, it's given 1300 degree K going into the turbine. Okay. Dashed line, irreversible and adiabatic turbine coming down to state 4A. We'll need to figure out how to determine that. And that will enable us to determine the work output of the turbine, W dot over M dot, and we'll go from there. That'll be all we need to do. So the approach, so rather than a laundry list of this step, this step, this step, let's look at the big picture. I've got a typo on my slide. It's an open system, not a closed system, okay? Open system. For the ideal gas, P times little v is RT for all ideal gases. The first law for our open system, Q dot N, so for any of these processes, Q dot N minus W dot out equals M dot times H going out of the open system minus H coming in to the open system. So this would be true for any of these components. Okay. Process 1 to 2. Let's tabulate Q in and W out. 1 to 2. No Q in for the compressor. W out, it's going to be less than 0. 2 to 3, the heat exchanger process. Q dot H, that's what we're looking for. W dot out, nothing. The heat exchanger is not lifting a weight. There's no shaft coming out of the heat exchanger process. 3 to 4, adiabatic. It's an adiabatic turbine, but irreversible. W dot out is going to be a positive number, W dot over M dot. 4 to 1, well, that's where we reject heat, and we're not even going to have to study process 4 to 1 to get everything we need to do in this analysis. So let's see. We are given W dot net. We're given W dot net. We're going to need to, that's 48,000 horsepower. We'll have to transform that into better units, but 48,000 horsepower is W dot net. We're asked to find the thermal efficiency. Well, we're going to have to get, we've got W dot net, we're given that, divided by Q dot H, which we're going to need to find. Okay. And so we only need Q dot H in order to find the thermal efficiency, as long as we get our units right. So a quick reminder about W dot versus little w and Q dot versus little q, because this is going to be throughout the solution. Remember, W dot, the power, is equal to the mass flow rate times little w. What will units of little w have? Kilojoules per kilogram. Okay. W dot, that should have units then of kilowatts. Same thing on Q dot equals M dot times little q. All right, and so looking ahead in the solution, W dot net is given, 48,000 horsepower. But what we're looking for, we need to find M dot. So if we can find little w net, it's easy to find M dot. So we're going to be looking for little w net. We're going to work through the analysis. So we're going to get little w of the compressor, actual. We're going to get little w of the turbine, actual. Okay. And we're going to get little QH, and that'll give us all the results we need. Okay, where do I start? A common question. We've got 4 components potentially to analyze. Where do I start? Well, there's several places you could start, but my recommendation is to look around. Where do you have both P1? Where do you have both pressure and temperature? Well, I've got it at state 1. P1 and T1 is given in the problem. Now, at state 3, we're given T3, but also we observe that P2 equals P3 for this heat exchanger process. So we could start there. I don't recommend it. I recommend we start at the compressor inlet. Traditionally, that's where we start when we're analyzing gas turbine engines. And now, so remember, for this example, we're going to treat air as an ideal gas with variable specific heat. So it's a little bit part of the crash course review. Remember, air, variable specific heat. Use table A22. There's a couple of columns that apply only to isentropic processes. And so we're going to use this column, P sub R, because for isentropic processes, we've seen in the textbook that P sub 2 over P sub 1, for this, let's say in general, P sub B over P sub A, but we have P sub 2 over P sub 1 equals PR2 over PR1. So we're going to be able to, this is what's going to enable us to get moving in our problem, is to use this P sub R term to get moving, to find what we need. Okay, so the first step in our solution is let's work at transforming our given net output power into kilowatts. So looking ahead, planning ahead, we're going to be better off by immediately transforming that given information into kilowatts. And so let's see, we've got 48,000 horsepower. I look up in the back of the book to see a conversion factor. 1 horsepower is 0.7457 kilowatts. And so we just sort of study that. And we say, okay, I see that I've got 0.7457 kilowatts divided by 1 horsepower. So I can multiply 48,000 by 0.74 to get 35.7 megawatts, or 35,794 kilowatts. And we're just going to leave that there. We'll come back to that. The next step, we're going to start at the compressor inlet. So we'll go to table A22, and we're going to look ahead. We know we're going to need H. We know we'll need an enthalpy. So we'll write that down. And looking ahead to study process 1 to 2I, the isentropic process for the compressor, we're going to write down PR1, 1.2311. We're going to write that down. That's going to enable us to study the isentropic process 1 to 2I, and our objective is to find H2I and T2I. Okay, so we refresh our memory. Here's P2 over P1. It's 32. It's given. Equals PR2 over PR1. Let's solve for PR2. Oh, there we go. Here's our numbers. So PR2 is the number 39.39. Let's go back to, and that's going to enable us to find T2I using table A22. Let's go look for 39.39. Okay, it's in between these two numbers. Here's PR in between these two numbers. We're going to have to interpolate to find H2I as well as T2I. And so here we go. Here's the linear interpolation in the solution. And so H2I, you see in my solution, I didn't even, I did the interpolation, but I didn't carry it out because I'm not going to be using it. What I really need is H2I, 778.85. That's key. We're going to need H2I. And why do we need H2I? We're going to use the first law to get the work isentropic for 1 to 2I. We're working on the compressor. Okay. So we're going to use that first law to determine W isentropic for the compressor, remembering that Qn equals 0 for the adiabatic compressor. So Qn, 0, minus Wi of the compressor equals H2I minus H1. Statement of the first law. So we've got all of our numbers from before. W isentropic for the compressor is negative 488.69 kilojoules per kilogram. What good does that do us? Well, next step, we're looking for the actual work required to drive the compressor. So we write down the compressor efficiency definition. My claim is you ought to be able to figure it out without going to a formula sheet or the textbook. The compressor efficiency is the isentropic work, Wi, divided by the actual work, Wa. Okay. It's going to take more work to drive the compressor than the isentropic situation. That's the way you figure it out. So the actual work is W isentropic divided by the compressor efficiency. So there we go. Here's our numbers. Negative 574.93 kilojoules per kilogram, actual work needed by the compressor, W dot over M dot. Next step is, well, we need to find H2A. So that's very critical. I've circled it. That's a very important part of net work. So that's a big accomplishment. Looking ahead, we're going to need to calculate the heat transfer in the heat addition process. So we need H2A. All right. And so we'll use the first law, since we just found the work actual of the compressor. H2A is going to be H1 minus the work actual of the compressor. That's the statement of the first law. Q, 0, minus W equals H2A minus H1. There it is. Oh, I see. I just wrote it down here. Qn, 0, minus WA of the compressor equals H2A minus H1. So H2 actual is 865.09 kilojoules per kilogram, a bigger number than H1. Makes sense. We're adding work to the ideal gas air. Okay, so now we're going to go to the next component, process 2 to 3, the heat added. That's QH. All right, so no work is involved. Let's see what we just found, H2A. We need H3, don't we? We need H3. We've got it because we've got the temperature. Enthalpy for an ideal gas is a function of temperature only. So we'll just go to our table A22, 1300 degrees K, write down 1395.97 kilojoules per kilogram. And looking ahead, we're going to study process 3 to 4I, the turbine isentropic process. So we might as well write down P sub R is 330.9. Okay, so we're going to do the numbers. We're going to apply the first law for the heat addition process. QH minus W, that's 0, equals H3 minus H2A. And so QH is 530.88 kilojoules per kilogram. Now we're going to move to the isentropic turbine. Isentropic process, P3 over P4 equals PR3 over PR4 using variable specific heat. So we'll solve for PR4, okay? This would be 1 over 32. P4 over P3 is 1 over 32, okay? So PR4 is 10.34. We're going to have to find H4 isentropic. So let's see, I'm going to go to table A22 and I'm looking for 10.34. It's almost tabulated, almost, but I'll do the linear interpolation to solve for H4 isentropic and T4 isentropic. So we'll just write down, we don't really need T4 isentropic for our work. You might in a test situation, okay? But H4 isentropic, 533.54. Okay. We'll write down H3 again from above to solve for the isentropic turbine work, W dot over M dot, using the first law, Qn, 0, minus W isentropic turbine equals H4 minus H3, H out minus H in. 862.43 is the isentropic work of the turbine. But we need W actual. We need W actual when we go back and look at the TS diagram. So we ought to be able to figure out what's the definition of turbine efficiency. Well, I'm going to expect to get less work out of an actual turbine than I would from the isentropic turbine. So the actual is simply going to be the turbine efficiency times the isentropic work. Once we get that, then we can solve for H4 actual, but we don't really need it, do we? So the turbine efficiency is 87%. W isentropic of the turbine, we just found 862.43. And so the actual work of the turbine is 750.32 kilojoules per kilogram. Okay. And it looks like this little text box here, it's interesting, but we don't really need to use it. Okay. So now we're to the point of we're near the finish line here. The back work ratio, we have now determined both the actual turbine work and the actual compressor work. And so here I'm tabulating here in my solution, W actual 750.32, and I'm also tabulating negative W actual, which is 574.93. So I'm recognizing that it takes power to drive the compressor. So my back work ratio is simply 574 divided by 750, or 76.6%. And so over 3/4 of the turbine output power goes to drive the compressor. That is a huge back work ratio. We want that to be as small as possible. And so this back work ratio is very important in the design and analysis of gas turbine engines. And this was one of the major problems all the way back in World War II, when jet engines were just being invented for aircraft service. And so the irreversibilities in both the compressor and the turbine were resulting in very, very high, let's say like 90% back work ratios. And so we've improved and improved and improved on that technology since World War II. So right now we're looking at 76%, 77% of the turbine output power is going to run the compressor. Very high back work ratio. Okay, thermal efficiency. We have everything we need for the thermal efficiency, the energy sought and the energy that costs. Well, the W net is simply the sum of the turbine work out and the compressor work out, which is a negative number. So W net is 175.39 kilojoules per kilogram. QH we found for the heat addition process, 530.88. And so the thermal efficiency of this Brayton cycle model for this real gas turbine engine is 33%. Wow, that's pretty bad, isn't it? It's pretty low. 33% thermal efficiency. Okay, now we were asked also in the problem, what's the mass flow rate and the heat addition rate? And so remember, W dot net was given. First thing we did was transform that into kilowatts because we got W net in kilojoules per kilogram. So W dot W dot divided by little w is going to give us M dot. There we go, see? W dot over little w gives us M dot, or 204 kilograms per second. That is a huge air mass flow rate for this ship blazing through the water. The rate of heat addition, well, we just got QH in kilojoules per kilogram. We just found M dot, and so we'll multiply these two together to get Q dot H equals 108 megawatts. That's huge. All right, now, example problem 2 is identical to example problem 1, except our ideal gas model is for constant specific heat. So we're going to be able to go through this a little faster than the first example problem. Just a little reminder of, for both variable and constant specific heat, we still have the ideal gas model, P times little v is equal to RT. We all have Cp minus Cv is equal to R for both models. But remember Cp, when we say Cp is constant, we need to just go look up Cp and hold it constant. It's a specific value, but it's a formula for variable specific heat. And that's why we have to use the property table for delta H for variable specific heat. But for constant specific heat, when we're looking to find delta H, this pulls out of the integral, Cp pulls out of the integral, so we've got Cp times delta T. I hope that in a nutshell gives you a reminder of these two similar but different ideal gas models, variable specific heat and constant specific heat. Okay. I made exactly the same mistake on this slide. This is open system, the approach, open system, steady state, steady flow. So the first thing we'll do for this example problem is we need to go find K and we need to find C sub P for air at a reasonable nominal temperature. And so I picked a nominal temperature of 800 degrees K. So I sort of eyeballed 1300 degrees K is the max, 290 degrees K is the min. So around 800 is what I picked as a nominal temperature. So I'm going to write down Cp is 1.099 and K is 1.354. All right. Same starting point. We're going to start at the inlet of the compressor. Okay, and then we're going to transform the net output power. Exact same approach. We still need W dot net in kilowatts, so exact same approach as before. Now we're going to study isentropic process 1 to 2i. So there's no more of this PR1, PR2 stuff. we've got to apply a very special relationship for an ideal gas undergoing an isentropic process, and that is P1V1 to the K equals P2V2 to the K. And then we can use that ideal gas equation of state and go through 4, 5, 6 steps, algebra steps to get T2 isentropic equals T1 times P2 over P1 to the K minus 1 over K. Look at that similarity. Here's that pressure ratio, but we're solving straight away for temperature, and that's what we need. Okay, and so here we go back to our numbers. We wrote down K. In my work, I like to go ahead and calculate the quantity K minus 1 over K, which is 0.261, and I write that down rather than having to do this on my calculator every single time. So that's my K minus 1 over K. Here's my initial pressure, 100 kPa, initial temperature, 290, the pressure ratio given, 32, and so T2 isentropic is 717.7 degrees K. Okay, we've got T2I. Looking ahead, remember why are we doing this? We're trying to find the isentropic work. The isentropic work for the compressor. And we're going to use the first law. And let's see. Oh, I didn't add this in my notes. Qn, 0, minus Wi of the compressor equals H2I minus H1. I did write it here in my solution. Well, what's delta H for ideal gas with constant specific heat? It's just Cp times delta T. Here it is. Excuse me for not writing it up here. Okay, so Wi of the compressor. Here's my T2I we just found. T1 was given. Cp we looked up. So Wi of the compressor is negative 470 kilojoules per kilogram. Now we're going to apply the compressor efficiency to determine W actual. Okay, I won't drag you through figuring it out. Again, same thing. We're going to divide W isentropic by 0.85 to get W actual, a bigger number, bigger negative number, negative 552.93. All right. So we are going to need T2 actual to study the next component, the heat addition component. So I'll use the first law to solve for T2 actual. Here's my note down here to find T2 actual, looking for T2 actual. Write the first law, Qn, 0 for the compressor, minus Wa of the compressor, just found it, equals H2A minus H1, which is Cp times T2 actual minus T1. So T2 actual is 793.12 degrees K. See how we're moving along in the cycle. Okay. Next is the heat addition analysis. We're going to use the first law. Simple as this. T3 was given. Okay. T2 actual we just found. Cp, we've already written it down. So straight application of the first law. QH is 557.06 kilojoules per kilogram. Cp delta T. Now we're moving to the turbine section. We're going to analyze the isentropic process first. Same isentropic, ideal gas, constant specific heat. PV of the K is constant. So we derive T4 isentropic is T3. P4 over P3, well, that's going to be 1 over 32 to the K minus 1 over K. So the same idea here. And T4 isentropic is 525. So we've got all these numbers from our previous work. T4 isentropic, 525.32 degrees K. Okay, so let's see. Isentropic work of the turbine. Apply the first law. I wrote down Cp from previous work. So the isentropic work is H3 minus H4 isentropic, which is, for constant specific heat, Cp times T3 minus T4i. So there it is. Isentropic work, 851.37 kilojoules per kilogram. Here's my little note about the first law. Look at this repetition. We're going to apply turbine efficiency to get the actual work of the turbine. Simply multiply the isentropic work, Wi of the turbine, by 87% to get a lower number. W actual of the turbine, 740.69. Got it. All right. So now the back work ratio, we just found W actual of the turbine, negative compressor work out 552.93. So the back work ratio for constant specific heat ideal gas is 74.7%, similar to the variable specific heat. Now, W net and thermal efficiency, same approach, just different numbers. So we're going to add up the turbine and compressor actual works to get 187.76 W net, kilojoules per kilogram. QH from the previous work we did, 557. So energy that sought over the energy that cost, thermal efficiency, 33.7%. Mass flow rate and heat addition rate. Same approach, just different numerical numbers, W net over little w net, to give us a mass flow rate of the air of 190.6 kilograms per second. The heat added, well, we just got m dot. We can write that down. QH we got from previous work, 557.1. So Q dot H, the heat added, the rate of heat addition is 106 megawatts. Wow. So the two examples, 1, 2. Let's compare those results numerically. Not going to certainly read the slide to you, of course, but recognize for our key measures of performance for our gas turbine engine, in order to generate a net output power of 35.8 megawatts, that was 48,000 horsepower. So do you see it's the same? We need around 200 kilograms per second. There is some variability there, 6%, 7% variability, depending on the ideal gas model, okay? But I'd say comparable, similar, okay? The rate of heat addition, about 2% variation. But in terms of thermal efficiency, only 2% variation in what we have for thermal efficiency, and about 3%, 2.5 to 3% variation in back work ratio. So for doing an overall analysis of an engine, which is what we were doing here, a little bit of quick and dirty, both of these ideal gas models are perfectly valid. You're going to get the same results, nearly the same results for both of these situations. Now, if you were a gas turbine engine designer, you probably want to go with that variable specific heat model. So let's go with a recap. Despite my blunders on a couple of my PowerPoint slides, the Brayton cycle analysis involves steady state, steady flow, open system analysis. The compressor and the turbine, or the compression and expansion processes, we can model as adiabatic and irreversible and apply compressor and turbine efficiency. The heat addition model, where we're modeling the combustion chamber, we're modeling that as a constant pressure process, which is a good model, okay? And the other thing to observe is for this gas turbine engine, the back work ratio is very high compared to a steam plant back work ratio. You could go back in your steam plant homework problems and see that the back work ratio for a steam power plant is a very low number compared to a gas turbine engine. And there's a lot of good reasons for that. And you should ask about that in your class. Why is that different? Why is the back work ratio different, so different for a gas turbine engine compared to a steam power plant? So that's what we've got. I tried to blaze through the second example problem simply to save time, but I hope that helps. I hope this helps your understanding of how we model gas turbine engines. Hope it's helped get you interested in gas turbine engine operations, and also compare what if we pick the ideal gas with constant specific heat model? Is there great variability compared to the ideal gas with variable specific heat model? And the answer is there is some. but not a whole lot. Okay, I hope to see you again soon, and keep up the homework problem solutions.